Hi, everyone. Thank you for joining us today. You can see my screen now,
Yes.
Mike? Yeah. My name is Natalie C., and I'm a structural engineer. I live just a little bit north of Berkeley. And joining us is Mike Horlick. Mike is a principal at Tipping. He lives at Boise, Idaho. I had a very chilly Christmas holiday. Hope you all stayed warm over the break. We're excited to start 2025 with a bang. This is our first full tutorial that we'll be hosting. And today we will be doing two examples. One of them is a reinforced concrete retaining wall. And the second one is in response to a question from one of our users on multi-story flexible diaphragm. But before we jump into the examples for tutorial part 7, um, Mike is going to do a review of part 6 tutorial. As you'll recall, we had done a 2D structural analysis of two different examples. The first one was a concrete beam demonstrating creep. And the second one, we had gone through an example for a concrete foundation with soil springs. So I'm going to hand this over to Mike. And just as a reminder, please, Mike, share your um, keyboard when you get a chance. Perfect. Thank you so much.
Uh, where's the There's the strip footing that big thing. Okay. So just reviewing the concrete beam with creep there. What we did last time was that we created a simple frame element, simple structural analysis model here. We defined some expressions with for the loading, some area loads, and then tributary width, and then calculated the dead and live load for those, and then we assigned those to the loading and our model. I changed the background to the white background color. And then we created our load sets, so Command LS, and we used the wand, with some dead and live load combinations. And then we assign those load sets to the loading. So those are all set up. And then we drew a cross section in a different layout, in a layout with a different annotation scale. So that has an annotation scale of 16. This is our beam cross section. We defined some fiber materials for the concrete and the rebar, and we assigned those the concrete to the outside concrete shape and the rebar to the rebar entities. And then we tagged that shape, bring up the modified properties sidebar, and we go in here to the entity tag field, and we gave it a tag XS. And then once it's tagged, we could create a frame element type, FET, and we clicked the new button, and we selected ACI, and we typed in our tag where it asks for the boundary entity, and then that created our frame element type, and it gives it the same name as the tag. I'm going to turn off the override colors for the fiber materials. Okay. And so now we have a frame element type that's defined based on this cross section that we drew as a fiber section model. If I double click on it, I can kind of see how it's meshed. And there are some properties inside here. The key thing is that for this creep example, we wanted to use nonlinear section analysis, which basically makes use of the fiber section as a set of nonlinear fibers, as opposed to doing like a equivalent crack section with a crack factor. And then we also wanted to include long-term creep so that we could see the effects of creep on the analysis. And having defined that, we made a viewport of this, Command VP, drew the viewport, and then we copied that viewport back into our default layout, pasted it on, and we scaled it by the ratio of the annotation scales, so 100/16. And so now we have an image of our cross section, and we assigned this cross section with the paintbrush to this the frame element type here. We have these multiple viewports showing for once the analysis is done. And once that's all set up, we push F5 to run the analysis, and then it does its work, and it comes up with the deflection of the beam considering creep. Now, one of the things that I noticed last time, there was an analysis that wasn't converging, and I went back in and debugged that and found out the issue. And one of the things I found was that we were being a little bit overly conservative with the creep analysis. So the deflection should have been more like 1.16 instead of 2.16 inches. And then this beam is sort of 259, over 259 is barely working with long-term creep. Maybe that's okay. But anyway, that's how the long-term creep analysis is done in Sketchulation. And then we also did an example of a simple strip footing. So these are all the tutorials that we've done so far. And here's our strip footing example. And in this example, we created a distributed spring. DIST is what I start to type when I want to make a distributed restraint like that. So there is the distributed restraint button, and we just outline, or trace over the the frame element that we're trying to support. So we've done that. We have to give that spring a stiffness, and that's defined using the subgrade modulus that you would get from your geotechnical engineer. And then we multiply that by the width of the footing to get a spring coefficient in KSI. So that's our spring stiffness. And then we assign it to our distributed restraint. And then we had we have a cross section here. This is our concrete cross section, and we had some loads. And then we ran the analysis, and we can see what the deflected shape is, and the moment diagrams, and the shear force diagram, and our DCR, and then we can get the total load supported by the soil, or the soil pressure really, by using the elEnv function. And we're specifying the ASD context and getting this is the keyword for the result that we're looking for. And again, if you're not sure what those are, you can type F1 and bring up the search and start to type frame element, and you'll see some options here, and one of them will explain to you all of the different results types that you can query. And down here is the one that we're using. So we have that, and then to get a soil pressure, we just divide that number by the width of the footing. And so we see that our at this location on the far left, we have a pressure of 6.93 KSF, and we can double check the total load from the soil using this other keyword SUMF right there. So those were the two examples we did last time. Any questions on either of those?
Mike, I just wanted to remind everybody that you need to add a roller,
Oh, yes.
at least a horizontal restraint when
Yes.
you're modeling this. And then there was another reminder, and that was that when you're using the distributed linear loads, you probably want to set it as compression only.
Oh yeah, that's right.
Yeah.
The distributed spring has some options to it, and one of them is the modifier. If you allow it to be to tension and compression, you can get a little bit of soil tension, which is not realistic. So I'll make that compression only.
Perfect.
Okay, so those were the examples from last time. I'll just close those files here and close that one. And that was our graphing tutorial from before. Okay, and so today we're going to do a retaining wall example, and I've already worked it up, and I'll show how we do this in a second. But what our goal here is to start with basically a retaining wall design and then use Sketchulation to do the analysis. So we'll go through that now. The first thing that I would do here is I would make a new document. And we'll usually want to start with an image of your design, whatever your sketch would be. And I just got this image from a PDF drawing. And so here's my image, and you'll recall that you can make the image transparent. So this is what it looks like when I just did the screenshot from the drawing. I usually like to knock it down so it's just faded in the background. And this is my retaining wall, and then I would double check to make sure that it's to scale. So I'll just draw a dimension line over that. And it's 13 feet, and that's what I expected. So I have a 13-foot tall retaining wall. Now, again, we always want to set up our page. So the annotation scale for something like this is probably not going to be what I have currently, which is 100. In this example over here, I already know 48 works pretty well. So that's a quarter-inch scale. So I would type in 48 for my annotation scale, and then move my page extents over to fit that drawing. And now I will go ahead and just bring in my loading. So I'll copy these things over here, and I'll put them over here and push Control V. Where did you go? Oh, way over there. I'm going to move everything over so kind of lining up with my previous example, like that. Okay, let's just go through this. So we have, I'm using this, it's just a few variables, H. So if we wanted to, we could draw H on here for the plan reviewer. We know that's 13 feet. So I'm going straight up with the angular constraint, and that's 13 feet. But I'm going to replace that and just call this H like that. So it's clear what I'm using. And then I've defined H over here in my expressions. I'm using a 1 foot strip of the wall, so that's why B is 1 foot. And then we have a water table situation in this condition. So the height of the water table is 1.5 feet. Water pressure at the base of the wall is just multiplying out the math, the B times the H water table times 62.4 PCF. Now you'll notice these expressions have comments at the beginning, and if you want to put a comment at the beginning of an expression, you just start to type your expression and say, I have a comment here, and I put a colon and a space, and now the program knows that my expression has this comment in front of it, and I can type whatever I want here, and it's not going to affect the expression. So that's how you put a comment in, is the colon and the space. And then I have some seismic pressure. Well, let's just see. I'm not sure I ended up using all of these loads, to be honest. So I just used unrestrained res 1. So some of these things I'm not going to need. So for example, the seismic pressure was something else. This is actually an actual job, and so some of these things are just holding over from that. So I won't need the seismic pressure. We'll talk about the soil stiffness. That's for my soil spring. And then we have our two earth pressures here. That's what I wanted to get to. So we don't need the seismic. We will talk about the soil stiffness. That's just for, again, the base spring. And then my two earth pressures, this came from the geotechnical engineer, defined this way. So W, the U is for unrestrained. So W, U at res 1. So I have a 1 foot strip there times a 30 PCF times big H minus the height of the water table. And so this is going to be the load at it's a triangular load, and it's going to be the load at the base of my wall. And then I have another load, again, because the water table, the geotech recommended that this is how it's supposed to work. Once I get below the water table, I start with my W U res 1, and then I add to it 23 PCF times the height of the water table. So we'll see that in our loading when I draw this up in a second. And then I've got my concrete strengths and my square root of f prime c. This is how you always want to do your square root of f prime c in order to get the units correct. So we take f prime c times psi, and then we take the square root of that, and then our answer comes out in psi the way that you'll want it, so you can use it in other equations. And then I drew these things out because you'll see that there's a development length issue that we have number 5 dowels that go at 6 inches on center for a certain height of the wall for 5 feet. And then we have number 5s at 12 inches above that. So that's what what these development lengths are for here. Okay, so now I'm going to go ahead and draw my retaining wall. Some of these things I'll just copy over. So I have several elements here that I put into this model. So these are my frame elements. There's several of them like that. I push Control C and go over here, and I push Control V and push the Enter key, and then they land where they were in the other document. Now I want to line this this up with the base of the wall here. So here's my base of wall. So I'm just going to push up my image and my dimensions, so it just kind of lines up a little bit like that. Okay. Now, again, why do we have several different element types in this model, and that's because the reinforcement is changing as we go up. We have down at the bottom fully developed number 5s at 6, and then we go up a little bit and we have partially developed, and we go up a little bit more and we have even less developed, and then we get above that the 5-foot line, and we have the number 5s at 12. So those cross sections, we'll create a cross section layout. And we do this because cross sections want to be drawn at a different annotation scale than the wall. So, cross sections usually want to be drawn at like 12. And so if we go over to my previous file, you'll see I have these are my different cross sections that are part of this analysis. We have this cross section here, which has number 5s at 12 on the one face, and then 5s at 6 on the back face. And we have a 3-inch cover for the back face. And then we have another bar. We go up to the next cross section where 2/3 developed and then 1/3 developed. So how do I deal with this? I make a number of fiber materials here. So if we look at where we're going with this, we have our rebar fully developed. And then we have our 1/3 developed rebar. So what I would do is I would start with the rebar material, and then I would actually change it into a generic material. And that way I can modify its properties. So 2/3 develop, or rather 1/3 develop, 20 KSI of a 60 KSI bar. It's pretty easy math. And then 2/3 developed would be 40 KSI. So I made these 2 partially developed materials, and then I have my cross sections, which are the concrete part of it is all the same. So I'm just going to make my life easy here and copy these things over to my other drawing here, and there they are. Now the fiber materials, when you copy from one document to another, the fiber materials will come along. All dependencies, layers, textiles, they come along with the copy and paste operation. So I don't have to redefine them, but let me just show you what it would have looked like if I would have done that. I would click new. I would start with a mild steel. It would start as 60 KSI, and I start that way because that fills out all of this information here to start with. And then I would then change to generic, and you see all the numbers stay the same. This is going to be a symmetric material. They stay the same. They don't change once I change it to generic. And now I can just edit it. Let's say this was 5/6 developed, so I could put in 50 here and 50.1. And then I could call this rebar, just for example, rebar 5/6. Okay, so that's how that works. And then I can always, if I want to make sure and compare these things on a graph, I can click the graph and see what my materials look like that way. Okay, so I had also tagged those cross sections. So this is the cross section tag ret wall 5,6. So it's 5's at 6. And this is ret wall 5,6, and then the 2/3, and then 5,6 to 1/3. And so then I go into my frame element type editor, and I already have these frame element types defined because when I copied over the frame element, it tried to bring over the frame element types. It couldn't do all of them because not all the cross sections were defined yet. So we'll have to go ahead and define those. So I go into this. This is my standard 5's at 12 cross section. I'll copy that and then paste this over to my cross sections layout, and then now my 5's at 12 frame element type all defined. So copying and pasting is usually pretty good at making sure that bringing everything over, all the dependencies, so that you don't have to redefine something in the new document. Now, when I go back to my frame, my structural model here, and bring up the frame element type editor and do override colors, I can see that these things are already assigned. So I have my retaining wall footing. Retaining wall footing was just a generic cross-section type where I entered in these values here, such as an elastic frame element type. And then I have my 5's at 6, 5's at 6, 2/3 develop, 5's at 6, 1/3 develop, and then 5's at 12 above that. Okay. Any questions on that so far?
Maybe a question for later, Mike, is if you
Yeah,
have different type of rebar on the top and the bottom, how do you know the orientation is
yes.
correct in your model?
Yes, good question. So in the frame element type, um, you will see you'll see you can double click into this and you can see where the bars are, and you can also rotate this with the angle input right there. And then the question would be, well, that still I can't quite tell what is positive moment versus negative. So you see you have your 2 and your 3 axis. One axis would be along the element, and then to see how those things line up in the frame element, I would go over to the frame element, and here I can there's a button to look at the cross section axes, and so here you see the axis 3, typically the strong axis, and then you can see that what the orientation of positive bending is. I'm surprised. I thought I had labeled this as axis 2, so I need to double check that. I'm not seeing that labeled here, so we'll need to add that label. But so that's how you'll know. And if you wanted this to bend in the other direction, you would put in an angle of 180 degrees in the frame element type.
Great.
Okay. Okay, so then I guess the next thing I might do is define my loading. So I have this water table issue, and we said the height of the water table was 1.5 feet. So I'll do LDL load linear, and I'm going to start at the base of the wall, which I've already defined here, and I come up 1.5 feet. Oops, and okay, so that's defined. The angle by default is going downward, and so I need to rotate that load. In the geometry here, I would give this an angle. By default, it's at -90, so it points down, but I'd put that at 0, and so now it points to the right. And then I will have an additional load, so this will be my soil pressure under the water table, and then I'll have also my water table, my water pressure load, hydrostatic pressure. So I select that grip and I push the C button to copy, and so now I have 2 loads. And then I will make another load, LDL, and go from here all the way to the top. And this is my standard soil pressure load, and again, that wants to be 0. Okay. Now, all of these loads are variable, so I select them and I check the box variable load. So now each one has an expression at each end, and I can enter these this way. So at the top we have 0, so that's a triangular load. This load here is going to be my W U res 1, like that. Okay. Now these get a little tricky because they're kind of overlapping, and I can also edit the expressions this way. Now you have to kind of remember which direction you drew from. So in this case, this is going to be the top load, so that's going to be my W U res 2, and I just copy this over and put this here and replace that with a 1, like that. That's a little bit of problematic to be able to tell which one's which. I think I got that wrong. It's supposed to be 2. Oops. It's supposed to be 2 here and 1 there, I think. Yeah, there we go. Okay, and then this one was my water table, my water hydrostatic pressure. This one I think is at 0 at the top. Oop, backwards. W W, and then 0 like that. Okay, now flips that the right way. Okay, so now I've defined my triangular loading, and the only fussy thing, this is something we may change where the program will automatically rotate this text so you can see it, but right now it's kind of overlapping on each other. And the only way to really change this is to temporarily go into the text style and just reduce the font height just for a second, just to kind of see where things are. Wait a second. That was not the right text style. This is supposed to be on my, what is this text style here? Yeah, it's expressions. I would have thought that if I changed this height, it would reduce this text, but it didn't do it. We'll have to look into that too. It's supposed to change that. Okay. In any event, we can see that we can kind of just graphically see how the loads are going, and we know what we've typed in. We can see in the entity editor what those expressions are, and so we're feeling pretty good about what we have, and we can also see the results to be able to tell what's there. Now we need to create our load sets. So again, we'll bring up the load set editor, and we'll use the handy thing here, the button, the easy button. We'll have our hydrostatic, or rather the earth pressure loading, the H, and the dead and live. We don't really have any live loading, so I'll just uncheck that. And so here we are left with our load combinations. And just do a brief check on the rest of these. They all look good to me. And I click OK. And now these guys are all lateral earth pressures, so I assigned them that way. Double check that they were assigned properly, and I'm good to go. So I've got my loading, I've got my frame element type. Now I need to think about supports. So similar to that other example with the footing, we'll want to put a roller support for horizontal at this slab. If I didn't have a slab here, if this was just a wall in the field, I could put a distributed spring to represent the passive pressure. So let me just demonstrate that. So I could put a distributed restraint like this, and by default it's pointing vertically. So I would go in here again to the angle and put this at 0. And so now, and just because of the way it's oriented, maybe I want to flip that. Actually, that doesn't change the angle. If I wanted to change the angle, I would go here and put in 180, just for appearance's sake. Okay, like that. And then I would have my other distributed restraint underneath here, like that. And now this doesn't require any roller or anything like that. It's perfectly restrained right now. And if I knew sort of a passive pressure stiffness, I could assign this. This can also be a variable stiffness. It can get stiffer as you go deeper. And for this example, I'll just assume that these are both the same stiffness, this gamma soil. And I will go ahead and make them compression only here and go to my expressions and type in the gamma soil like that. And so that now those are all defined, and I should be able, as far as I can tell, I think I should be able to run the analysis. I click F5, and I can see that it ran. I bring up the structural analysis options, and I can see the results that I have. I can double check some things, just for quick checking here. You can see my moment diagrams. I have these colors that are being overridden by the frame element type. So I can look in and at what my moments are. I can see what my overall deflection is. And basically, have a good understanding of what the model's doing. And now if I feel good about that, I would go ahead and make my viewports for the rest of the results for printing. So this is my retaining wall. Oops. I wish I could type today. Retaining wall example. Okay. And then I will click on this and I'll do an add page. Add makes my new page here. And then I'll do the viewport model command VPM, this, and it shows all of the results on top of each other like that. So I can kind of see. I'm going to guess that probably my viewports will be good enough if I go about like that size, let's say, and decide what I want to show. I'll want to show the factor loads and reactions, maybe just for the dead plus H, and the deflected shape for all the ASD, and then I want my DCR, and let's say my moment and shear, like that. I click OK, and bring these guys over, say like this, and enter to scale them. So now I see not everything fits on one page. I might make some changes here. So one of the things we noticed, we can look at the reactions under dead plus H. So I'll just pull this viewport down so I can see all of this. Now I don't know if I have a great design. It's four kips per foot, and these are 1 foot strips. So that's 4 KSF. Maybe that's acceptable, maybe not. But then I can see my passive pressure, the way that this is working. I can see my deflected shape for all the ASD combinations with I think it's just the one. So it's 2 inches of deflection. I can see my DCR is 0.65 down near the bottom. And I can double check my moments if I want to, and my shear force. Yeah, the shear force might be an important thing to check too, to see if this cross section really works for sliding shear at the base. That might not be something that we're checking. Interesting thing you'll notice is that the loading is taking into account self weight, so that there's actually a vertical component of the load that slightly helps the concrete cross section in this analysis. If this were for production, I might make some viewports for my cross section. So just demonstrate that really quickly. Make a viewport here, like that. And again, this is at 12 and a scale of 12. So then I would put this in, and if I was going to make this a true scale, I would scale this by 48 over 12. So these are my cross sections like that, and I can decide to say not draw the viewport boundary like that. So these are my cross sections. Another thing that I'll show you here is that when you have a viewport, you can actually pan inside the viewport. So I want to show that other cross section that's up above here. So I pull this viewport over, I select the viewport, I type VPZ viewport zoom, and then I can actually pan within the viewport. And right now it's empty, and now it's not empty any longer. And so here's my other cross section there. And then I click escape to get out of that command. Now I can see my cross sections. And then I might just massage these things a little bit, maybe make another page. I just did a copy command here. That's fitting on this page, and then maybe I want to pull this guy over a little bit so it fits on the page. for that one, for that one. And now I'm pretty good to go. Set up my print area. It's already auto set and ready to print. Okay, any questions on this example? No? Okie doke. I will go ahead and save this.
Great.
And tutorial today. Tutorial retaining wall. Um, 31. Oh no. Okay, that's that. Now, what I wanted to show, if there's time, might not be time, is this multi-story flexible diaphragm. Natalie, I think it probably would be best to hold off and do that at another time.
Okay. Yeah.
And just and end a little bit early today. Juan or Mohammed, do you have any questions before we wrap up? Okay. This is a preview of what we will be getting to eventually, how we have a diaphragm that we're looking at here. We lay out some walls, and then we have several levels that need to stack. So we'll take the reactions from one level, bring them down to the next level, and stack them all up so that by the end of it, if the loading changes or something, it's all sort of linked together, and you can stretch the supports and walls around in any way that's necessary. So that's what we'll do next time.
Great.
Okay. Great. Thanks, Natalie. I hope the rest of you have a great day, and feel free to let me know if you have any questions or thoughts along the way.
Thanks. Any questions from Mohammed? No? Awesome. Thanks, Mike.
You're welcome. Have a good rest of your day.
Bye.
Bye.
Thank you.